Now it's time to start another chapter. This chapter is about software issues for additive manufacturing. And in this chapter, we'll be discussing some issues related to the CAM software, related to STL files, or some modeling problems. As you know, we discussed that in the second chapter, in the generalized pipeline of additive manufacturing. We make use of, at the beginning of this pipeline, CAD software to design some parts which are to be fabricated on the additive manufacturing machinery. And then what we do, we convert these models into an STL file, which is composed of some meshes, and it just have an information about the external geometry. As you know, we don't have anything related to the interior. And sometimes some people say it's the abbreviation of stereolithography, and some people say that it's the abbreviation of stereolithography tessellation language. What is tessellation? We are tessellating triangles on the boundary of the surface. So we are distributing triangles on the outer geometry, and that's why they call it as an tessellation language, and which is only used for stereography method. But it's not true. As you know, we can use the same file for different purposes. Another issue about STL files, as you know, since we are trying to represent the surfaces by using triangles, the accuracy is affected. Let's have a look at here, for instance. Once you have such an arc, and if that's the resolution of your triangles, then you see that we have lost information, we have lost accuracy at these regions. So the triangulated version is not as accurate as the original version. But if you use many triangles, let's say, if you use more triangle than the previous case, then that means you are increasing the accuracy, but still, even you use infinite number of triangles, it will not be as accurate as the original geometry. But obviously, you can increase accuracy as you increase the number of triangles. Let's go into details of the STL file formats. Since this was your homework, you have already studied, I think, on the file format. We have two versions, the binary version and the ASCII version. In the binary one, the information is represented by using some, let's say, binary values. Okay. And if you open a binary STL file using a text processor, you will see that these letters are represented with some unmeaningful, let's say, letters. You will see such expressions in the binary STL file format. But if you save your STL file in Do you hear me now?
Evet hocam, şu anda geliyor.
Evet hocam.
There happened a problem. Let me share it once again. Is everyone here? I think here. Okay. Oops. Okay. And we said that in the STL file, as you know, there are triangles. And in the definition of the triangles, we need to have 3 vertices, and we need to also have a unit normal vector. we need to have this normal vector so that we will understand whether that side of the triangle is representing the outer or the interior of the part. So that's why it's important, and we need to have the normal vector in our file. Another issue about the STL file is that we don't have any dimensions. You'll see that in the content of the file, we don't write anything related to the units like millimeter, inches, or meter. It's not important in the STL file. But for most of the time, the software are assuming that the dimension is in millimeters, but it's not a must. And some of the default, let's say, STL viewers, you can easily switch to different dimensions. And for each triangle, we need to have, as you know, 12 numbers. What are they? We need to represent 3 vertices and a unit vector. So we have 4, let's say, kind of vectors. And in each vector or vertex, we need to have 3 coordinates. That's why if you multiply 4 by 3, we need to have 12 numbers for each triangle. And in the additive manufacturing, we have other formats. And in the homework, you are also discussing, you are focusing on additive manufacturing file format. But I'm not going to focus on other formats. In this lecture, I will be just focusing on the STL format. Here you see a simple tetrahedron, which has obviously 4 faces, 1, 2, 3, and 4 underneath, 3 on the sides, and 1 underneath. And in the STL file format, we are always assuming that the left bottommost corner is our origin. We can say that this is the point 0, 0, 0. And so that's why this is x-axis, this is y in our example, and this is z. Since we have 4 faces and it's a very simple shape, tetrahedron, so we can easily represent each surface with a single triangle. Here you see we have the first one here, second one, the third one, and the last one. And at the beginning of the file, we have such a definition. It says that it's a solid shape, and the name of the shape is triangular pyramid. And then after you define all these triangles, you end your definition with an end solid term. But the interior is, as I said, just composed of the definitions of the triangles. Let's focus on one of it. At the beginning of the triangle definition, we write the normal of the facets. This is the first value, x, y, and z. So these are unit normal vectors, which means that you cannot have values greater than 1. And then after the normal is defined, you start writing the vertices. And this is our, we have another term, outer loop, which means that the loop for the triangle is just started. These are the vertices, and then after the vertices are defined, you simply end the loop, and also you end the facets, which is the triangle we are working on. So let's focus on this triangle. The first vertex is 0, 0, 0. Yes, it's here. And the other one is 1, 0, 1. So this is here. And we usually prefer to have a counterclockwise, let's say, rotation while we are putting numbers after each other, but it doesn't matter. Since we have normal, it's not a problem. So this is 1, 0, 0. But as you see, this is not the point actually we are discussing. Or is it? Let me see. This is 0, 1, and 0. It's not the one actually inside this triangle. Let's have a look at this one. And I'm assuming that we have right angles here. So it's 0, 0, and 1. So which surface actually this one is referring to? This front surface. That's the front triangle defined here. Another one, 0, 0, again the origin, and then we have 0, 1, 0, and 1, 0, 0. So it is that the bottom, right? The bottom triangles. And let's have a look at, I didn't focus on the normals. Let's have a look at this one. The front surface, its normal is 0, minus 1, 0, which means that the normal is in the minus y direction. Is it that? Yes. If you look at the front triangle, the front surface face, it should be directing towards minus y direction. And it is written here, the normal is 0, minus 1, 0. And then let's have a look at this one. We covered the vertices, but let's focus on the normal. It says that the normal is in the negative z direction. Since I said that this is the bottommost triangle or the base triangle, and obviously it should be pointing downwards, which is minus z direction. And then let's have a look at this one. We start with the origin, 0, 0, 0. Then I have 0, 0, 1, which is here. And then the last point is 0, 1, 0. So it's the side surface, this one here, actually. Right, 0, 0, 0, 0, 0, 1. This is here. So this is the first one, second one, and the third one is here. So what about the normals? Do we have a problem here? Any comments, guys? Is it fine? If it's fine, then I am continuing. So let's have a look at the other one. This time we have 1, 0, 0 is here, 0, 1, 0 is there, and then we have the other one, 0, 0, 1 here. So this is the let's say rightmost face. Okay. Since it's inclined, that's why we have a normal vector in all x, y, and z directions. It has components in x, y, and z directions. So in the STL file format, we have some regions reserved for the header. In that header, we have information related to the definition of our model, and 80 bytes are reserved for that. And then we need to have some 4 extra bytes for the number of faces, how many numbers of faces are available in this file. And then we need to have 50 bytes for the record of faces. What are they? We need to have 3 for 4 bytes, which makes 12 bytes for the normal. Since we are using 4 bytes for each number, and we have 3 numbers for while defining the normals. And then we need to have some information for the vertices. Since we have 3 vertices, in each vertex we have 3 numbers, and for each number we need to have 4 bytes, which makes 3 by 3 by 4. And additionally, we need to have an extra bytes for controlling whether we have written the correct information, and that makes actually 50 bytes. So this is the size of the file actually. And how do we create the STL files? That's very simple. As you know, you simply save it as an STL file in your CAD software. In most of them, your CAD software asks you the resolution of your model by setting it to, let's say, 0.01 millimeter or 0.1 millimeter simply. You may play with the number of triangles which are going to represent your original model. And we know that if you have less triangles, the size of triangles becomes smaller, then the approximation will be better. But if the number of triangles is less, then the quality will be lower. And as you know, in the cubes we have 6 faces, and you can simply represent each face with 2 triangles, and that makes 12 triangles for a given box shape. And while saving, actually we are trying to decrease the gap between the original surface and the approximated surface. You may have different approaches, but in such cases, it's better you have as many triangles as possible. Here you can see our famous example, the cup shape. And once your triangle size are larger, this is, as you see, a rough approximation. But on the right-hand side, we have a better approximation. You see the side, the length of the triangles are decreased, and we have a better approximation, and we have less error in terms of the approximation. So now let's focus on slicing, which is the biggest issue actually in additive manufacturing. Without slicing, you cannot do the manufacturing in additive manufacturing technologies. So we'll spend some time on the slicing, how we do it, what are the type of algorithms, and we will be going into details of these methods. So what we obtain in slicing, we usually, for the conventional additive manufacturing technologies, we do slicing in XY planes. So after you have the part, we take some intersections of that part with the various XY planes. So once you do that intersection, the triangles actually will be intersecting, some triangles will be intersecting that planes, and that intersecting region will actually be contributing to the slice. Assume that this is the front view of a triangle, and once you do an slicing at this height, let's say, this part of the triangle will be important for us, and it will be the part of the slice, and we need to compute that region. So what we are going to do, we will be using some algorithms to find these contours. Let's have another triangle here. Another one. What we are going to do, we will try to find all these intersections. This is the first, let's say, line segment. This is the second one, and this is the third one. And if you look at from the top view, we will have such segments, right? We have another one. I'm assuming that this is a kind of an layer of a specific part. And the thing is that they will not be usually in order, okay? So we may have such random orders. So that's why after you obtain all these line segments, we need to find a proper way to join all these segments in a, let's say, counterclockwise manner. So that will be the second part of the algorithm. We should first find the intersecting lines and then order these lines into a complete outline. That will be the end of actual slicing. So now let's focus on the first part of the algorithm. This is for actually obtaining the intersecting parts. Now I would like to go through one by one how do we start the algorithm. This is the flow chart of the slicing, or flow chart for the first algorithm to obtain the intersecting lines. So what we do, we simply start reading this STL file, read the name of the model, and check how many number of triangles are available in the files. And then after we get this information, we start scanning all these triangles. So faces is a triangle. We have a kind of a for loop here. We start processing each triangle one by one. And then what we do, we get the vertices of that triangle. And since we know the cutting plane, we know the information about the cutting plane. So what we need to know the z value of that cutting plane. And then we compare the vertices with that cutting plane. So if, let's say again, this is a triangle we are working on, we have the vertices, we have the information about these vertices, let's say, and this is a second one. And finally, this will be the third vertex. Okay. So any idea how we can do this comparison? And how we can decide whether our, let's say, intersecting plane is, slicing plane is intersecting with the triangle or not. Obviously, this one is intersecting, but the other two are not intersecting. And how we can do this comparison here and then move on. Any idea, guys? Any idea?
We can compare the lowest z value with the plane.
Yes, the easiest thing is actually compare z values. We have a z value for the slicing plane. Let's say this is equal to A, this is equal to B, and this is equal to C. So we can check whether these z values, since in this triangle we have a maximum z value and a minimum z value. What are they? For our triangle, this is this should be in between z1 and z3. If the slicing plane has a z value which is lower than this range, then we will say that there is no intersection. And if it's higher than that value, that range, we will again say the same. There is no intersection. But if that z value is in between this range, in the range, then I can say that there is an intersection. So I should continue to this operation. What says here that, what is written here is that store the intersection line of these facets with the plane. So what I do, this is the intersection, and I need to compute this intersecting points. This is the starting of the line segment, end of the line segment. So I need to store this value. Let's say I have a value for x, let's say for y4. And I don't need to store z since they will have the same value with this slicing plane. And this is x5 and y5. I need to store it somewhere so that later I will process these intersecting lines, intersecting portions, and try to join them together so that I will have the proper complete contour. And then what I do, I continue here. Are all the faces scanned? If you are at the end of your STL file, then the answer might be yes. If that's the case, you will be done with this algorithm. But if you have still faces, if you have still triangles which are not checked yet, then you should start the scanning once again. So you will be doing these operations for the number of faces. After you obtain all the intersecting, let's say, portions, and you may stop this process and you will say that all the intersecting portions at that specific z height is obtained, and I can start the other algorithm. So please, Umut, write your problem as an email. This is not related to lecture. Please don't send anything into chat area. We are focusing on a different topic. Okay. Okay, guys, do you have questions regarding this algorithm?
Hocam ben bir şey sorabilir miyim?
Yes, Ali.
Bu üçgenleri yapıyoruz. Üçgenin 3 tane köşesi var. Yani mesela bir tane z plane'imiz üçgenin ortasından geçse bile bu şey yapmıyor değil mi? Yani oradaki o x, y değerlerini alabiliyoruz gene de. Yani üçgenin ortasından geçti şu an. Mesela büyük bir üçgen düşünelim.
Okay.
Yani oradaki o şey değerini alıyor değil mi yani? Üçgenin köşe noktalarından geçmek zorunda değil yani, değil mi? Onu soruyorum.
So we may have an intersection here. We will consider these points. If you are passing right at the middle here, then we will store these vertices. If it's here, we will store these two vertices. Okay? I'm not sure that I got your question correct or not, but this is how we are going to do.
Tamamdır
if you
hocam.
are passing from the top, then you should only consider the vertex, not a line segment, but you should store a single vertex.
Tamamdır hocam, sağ olun.
So this is what we do in the first part of the slicing. For that given plane, we need to consider all these triangles and check whether there is an intersection or not. And after you see all these lines, then in the second step, we will see we will be ordering all these line segments together properly so that we will have a continuous contour. Yes, Shafak?
Bu atıyorum tek bir cutting plane için bütün STL'i tarıyor mu?
Yep. But you may have some limitations. For instance, if the z value is not closer to your height, then you may disregard them.
Okay.
But in this flow chart, as you see, it's covering all the triangles, and it will take obviously some time.
Okay, thank you.
You're welcome. Any other questions, guys? Okay. Let's switch to do some details. So now I will focus on to this part. How we are computing the intersections, intersecting points. As the most time-consuming part of the algorithm is this box. We will be checking, we will be calculating the intersecting points with the slicing plane. So we have actually 5 scenarios, as you see here. Some of them are very simple, some are complicated, especially the last one. So we will spend more time on the last one, but the first 4 are not that complicated. I will focus them one by one. Let's have a look at the first one. It says that all the vertices of a triangle lie above or below the intersecting plane. So it's not that complicated. We have such a triangle. And it says that the intersecting plane is below or above the triangle. So it means that we don't need to spend more time on it. We can simply ignore this triangle. It's not intersecting with the given slicing plane. And then the second case, a single vertex directly lies on the plane. So this is actually the case. So this vertex is lying on our slicing plane. What it says is that obviously we have an intersecting point. We don't have a line segment, so we can simply ignore it. Since the thing is that this point actually should be stored while we are dealing with other triangles, okay? since if you consider this triangle here, when we do the intersection, we will have such a portion, and that point will be stored while we are dealing with the second triangle. So we can simply ignore again this vertex, this single point. And then let's have a look at the third one. The two vertices simply lie on the plane. So that might happen. Now I will draw this case. Assume that this is our triangle. And if we have such a slicing plane, which is going through our line segment here, so we can say that one line of the triangle is contributing to the contour, and which means that our intersecting plane is going through one segment, one part of the triangle. So as you see, one edge of the triangle will be part of the profile. So we can simply take that edge and store it into our list. We don't need to do more computation. We can directly store the coordinates of these points. And then let's have a look at the other case. It says that there might be some situations where three vertices might be lying on the same plane, on the slicing plane. This is a very rare case. Assume that you have a kind of an tetrahedron like this one. This is a kind of a tetrahedron. As you see, we have four surfaces, and we are saying that this top surface actually on the slicing plane. This top surface is on the slicing plane. So what we are going to do, if that's the case, we will simply take these vertices, and all the edges of the triangle will be the part of the outer profile. So if you look at from the top view, we will obtain such a contour. This is our result after you do the slicing, and the edges of the triangle is directly contributing to the contour. This is top view. And this can only happen if your part is kind of a tetrahedron, or if the top surface or the slicing region is composed of a single triangle. If that's the case, again, you don't need to do any computation, and all the vertices of your triangle will contribute to the contour. But there might be another case here. Assume that you have more complicated planar surface at the top. Assume that this is the top part of your 3D shape, top surface. And in that top surface, we will have numerous triangles, okay? Triangles at the interior, on the sides. You'll have many of them, okay? So here it says that if you have triangles which are on the plane but have no edges, no actually vertices on the boundary, then you can simply ignore these interior triangles. But obviously, if you have triangles having some vertices on the edge of your surface, then obviously they will be contributing to the outer profile, and you need to store them. But the ones having no connection with the outer boundary can easily be ignored. Let's have a look at the formal definition here. Three vertices lie on the plane. This is the case, yes. All the vertices are on this slicing plane. But as we have seen in the first case, let's say this is the case 4.1, and this is the case 4.2. If that's so it starts from here. So this is actually 4.1. This is 4.1. It says that the whole triangle contributes wholly to the profile. Yes, that's it. This is 4.1. We have a single triangle at the top surface and it's wholly contributing to the profile. But if you have a larger and a bit complicated top plane, top surface, then that means some of these triangles might be included in the outer profile and some may be disregarded if they don't have any connection with the outer profile. Okay, this is the fourth case, fourth scenario for the slicing, and it's more complicated than the first three. Any questions, guys, regarding the fourth case? As I said, it might be a bit complicated, so if you have questions, please feel free to ask, and I may spend some more time on discussion of the fourth case.
Hocam 4.2'yi bir daha açıklama şansınız var mı acaba? Biraz karışık geldi de.
Okay, I may maybe draw it on a paper here and try to show it a better way. I'm trying to do it quickly. So that means switch to the full view. So you see, this is, we are assuming that this is the top surface of the part, okay? So since the fourth case stating like that, you have a slicing plane, and the slicing plane is matching with your top surface. So if that's the case, we are saying that in 4.2, if you have some intermediate triangles, you can simply ignore them. So these will be ignored, and we will consider just the triangles having connections with the outer boundary. But I will not spend time on the computation of the interior triangle. They will be cancelled, but I will do some computation with the triangles on the boundary. It's okay now?
Evet hocam, teşekkürler.
You're welcome. Any questions, guys? Any more questions about the fourth case? As I said, it's a bit complicated. Feel free to ask anything related to this fourth case or the previous ones. Okay. And then we have the last case for the slicing. This time it's about the main intersection, actually. Now let me, oops. Let me clear this part, screen, erase pen, yes. And I will switch to, yes. So now we will be focusing on the last case. This is a real intersection. I can say that we have a triangle like this one, and this is our slicing plane. Now we will spend some time on this kind of intersections. So what we are going to do in such intersections, we need to determine these intersecting points. Once you obtain these intersecting points, then you can simply define a line segment between these points, and that line segment will be contributing to the outer profile. So that's it, actually. This is the fifth case. So what we have done here is that we have projected that triangle onto first y is equal to 0 plane, and if that's the case, then by doing some calculation, we can determine the x value of that intersecting point, okay? So this is our intersection plane. We have the vertices of the triangle, and since this is y is equal to 0 plane, we have done a kind of a projection. So they all have y value equal to 0. So we make it simpler, and we can use simple math equations to determine the intersecting point. We already know the z value since this is the intersecting plane. we should be knowing that z value, and we also know x2 and z2, they come from the definition of the triangle x1 and z1, and furthermore, we know z1, but we don't know xi here. I'm sorry, not z1, zi. We need to find this xi value. So how we can find this value? We can simply do an interpolation and try to compute this xi value. I'm not going to do it here, but it's not that complicated. We can use simple equations and find the xi value. And then later what we are going to do, we will do the similar things for x is equal to 0 plane. We will project again our triangle onto x equal to 0 plane. And this time we will be calculating yi, and we have already determined xi. And then in the second case, you will determine yi, and we already know zi. So the intersection point is now already calculated. And we can do it for the other part of the triangle and determine this intersecting, let's say, segment. After you find the coordinate values of these 2 points, we can store it into a kind of a list so that later we can work on joining of these line segments together, and finally we will have a proper contour. Any questions, guys, about the details of this fifth case? No? Okay. So this is actually the second part. In the second part, we are trying to join these line segments so that we will have a continuous contour in that plane. So what we have at the beginning of the, let's say, algorithm, in the second algorithm, we have a kind of a list of line segments. Since for each line segments we have 2 points and we need to have their coordinates. So in these in this list, we need to have some coordinate values of these line segments. But as you know, they are not in order, so we will be checking their orders and try to find the closest one to a specific one and try to join them one by one. So what we do at the first step, we select a line, assume that this is the first line we selected. This has a kind of an, let's say, a tail and a head, or I may draw it here. Yes, this is a tail of our first line segment, and this is the head of our first line segment. And we know the coordinates of this first selected line segment. And then what we do, we simply store it into a new and empty, let's say, list of lines. This is stored here. The first line segment is end and starting points are stored. And then what we do, we compare our line segment with the rest of the line segments in our given list. We check the distance between the tail. This is a tail. We check the distance between the tail of this line segment with the others. As you see, there are many line segments here. We check the distance of our tail with the coordinates of the other line segments. And then we try to find the line segments which should actually have a 0 distance between the tail and the corresponding line segment. After you find it, then what you do, if that point, let me draw it here. Assume that we have a line segment here. This is the start of that new line segment. This is the tail of it, and this is the head of it. If you find that, let me draw it again. This is actually the line segment we are working on, and this is the other one. And if you find that the distance between the tail of the corresponding line segment is 0 with the head of this line segment, then what do? You simply connect this actually head of this new line segment to the tail of the other line segment. So there should be a kind of a connection. By doing some proper swapping operations, you should check whether the head of the new line segment is matching with the tail of our corresponding line segment. If they have a distance, if they have a gap of 0, let's say, then you can simply say that they should be connected to each other. And you should simply store it into the new list as the next item. So this is what we are going to do while comparing the line segments in the given list and try to join them together. And at the end of the algorithm, we will have a proper contour, and this will be a continuous contour. Yes, Shafak.
Yani bu line segmentler tek bir Z içinde yapılıyor değil mi? Yani
Yes, in the previous algorithm, we determined all the intersections on a specific plane, and here all these line segments are on the same plane. So we are working on a specific height. We don't need to consider the Z values. They are on the same plane.
peki burada tail ve head'lerin arasındaki distance'a bakmaktansa direkt eşit olanları arasak daha kısa sürmez mi?
What do you mean
Yani
by
veya böyle bir yöntem var mı?
we don't have any equal, let's say, line segments? They are different.
Yo hayır, hani bir line'ın tail'i ile diğerinin head'i arasındaki distance'lara bakıyoruz ya.
Yep. We are
Sadece
also checking not the tail, we are also checking the head. If you find that this one is better, you can do some swapping operation. You may swap the head and the tail of that is here, as you see here.
anladım.
In such cases, you may switch the head and the tail.
Peki, teşekkürler.
After you do it, if you don't need to do any swapping operation, you can directly store it into the new lines list here. But as your friend pointed out, if there is a mismatch between the tails and the heads, you can do some swapping operation. So after you check all the lines, then what you do, you store them into the list, and that means you are done with the contour, and you can finish this algorithm and output your contour.